Okay. Okay. We finished the class yesterday looking at the polarity of the bonds, and the bond polarity, when you're talking about just the bond between two atoms, it depends on the electronegativity, difference in electronegativity. If the electronegativity is the difference in electronegativity is less than 0.5, is going to be non-polar, essentially non-polar. If it's between 0.5 and 2, is going to be polar covalent, and if it's greater than 2, is going to be ionic. But in general, we talked about metal, non-metal being ionic. Two different non-metal, it would be a polar covalent, except with the carbon-hydrogen bond that I emphasized a few times, that is a non-polar bond, essentially, because the difference in electronegativity is almost 0, is much less than 0.5 between carbon and hydrogen, and all organic molecules that they have only carbon and hydrogen, they are non-polar. That includes alkane, alkene, and all hydrocarbons with no other heteroatoms. They are non-polar. So when we look at the polarity for the molecules, we first have to have the Lewis structure. So if we have Lewis structure, then we can look at the vectors to see if they cancel each other, because they are pulling electrons away. If there's higher electronegativity, it's going to pull electron away. And then you have the vectors. I said vectors 2 times, but it only makes sense to people who already have physics, most likely. But if you didn't have physics already, then you have to learn about vectors first before you can do the calculation, or before you can predict if the molecule is polar or non-polar. But what we are going to use is a shortcut to that. It's like you look at the structure formula. You look at the Lewis structure for your molecule, indicate your central atom, and then check the domain atom. If the domain atoms are all the same, the molecule is going to be non-polar. If one is different than the other 3, then your molecule is going to be polar. So mu equals 0. Basically, dipole moment for molecule, or polarity of the molecule, is 0 if all electron domains, those are the groups or elements that are directly attached to the central atom. If they are all the same, your molecule is non-polar and the dipole moment is 0. If you have pair of unshared electron on central atom, your molecule is going to be polar, because pair of unshared electron, as we talked about yesterday, it counts as electron domain. So it's not the same as the group or other element that is attached to the central atom. So this molecule here is polar because chlorine is different from 3 hydrogen. Hydrogen is different from 3 chlorine, and the second molecule. And the third molecule, you have all chlorine, so it's non-polar essentially. The lone pairs make the molecule polar. So if you have lone pairs on the molecule and the central atom, then your molecule is going to be polar. For organic molecules, when you have a polar bond in the molecule, so that is like carbon-oxygen bond, carbon-chlorine bond, CH3Cl, it is polar actually. CH3Cl, that's this molecule up here, and that is polar because Cl is different from the hydrogens, so it's going to be polar. But Cl4 is going to be non-polar. So mu equals 0 means non-polar. Mu, if it's greater than 0, that means your molecule is polar. Very good. So if you have a CN bond in the molecule, CO bond, or C halide, CX, X is used abbreviation for the halide in organic molecules, and that is any of the group 7 elements. That would be chlorine, bromine, iodine. If you have in the molecule, your molecule is going to have a polar side to it, so it's not pure non-polar compound, unless it's a molecule like the tetrachloromethane, which all the groups are just chlorine and they're all the same. But if you have one of them or two, your molecule is going to be polar. Why are we concerned about polarity of the molecule? Because we talked about, also we mentioned yesterday, the polarity of the molecule is going to predict the behavior or physical property of the molecule. Molecules that are polar, they are going to be more soluble in polar solvent. Molecules that are non-polar, they are not going to be soluble in water in general, because it's a polar solvent. And the other factor for solubility, since I mentioned solubility, is the size of the carbon chain or number of carbons that you have in the molecule. So if you have a polar compound, let's say if you have a compound that is carbonyl compound, so you have a CH3, CH3, two CH3s attached. This molecule, is this molecule polar or non-polar? This molecule is polar because you have your CO double bond here as a polar bond, and you have a small carbon chain. The carbon chain is less than 4, so you have only three carbon here. This molecule is going to be soluble in water also. It's polar and it's soluble in water. But if you have a molecule that it contains CO double bond and it has 5 carbon, this molecule, it's going to be a polar molecule because of the CO double bond that you have there, but it's going to act like a non-polar molecule in terms of the solubility, is not going to dissolve in water. So if you have a polar molecule that contains CO double bond or carboxyl group of COOH for carboxylic acid, or alcohol, it contains OH. So these are molecules that they're oxygen containing molecules. They're polar compounds. They are going to be soluble in water if they have less than 5 carbon in their carbon chain. If it's greater than 5 carbon, it's 5 carbon, the solubility drops like significantly. But if you have more than 5 carbon, it's not going to be soluble in water, because the long carbon chain, it takes the priority over the polar functional group, and your molecule is going to act as a non-polar molecule to end up with. So the polarity of the molecule is going to affect the melting point and boiling point as well as the solubility. Boiling point is going to be higher for polar molecule compared to non-polar molecule. The melting point the same, because polar molecules are going to have dipole-dipole interaction as their intermolecular forces. So London dispersion is specific to nonpolar molecules. So nonpolar molecule, if your molecule is nonpolar, is going to have only London dispersion intermolecular forces. Now, hydrogen bonding, it's for molecules that contain 3 specific bonds. If your compound contains HF bond, NH bond, or OH bond, only these 3 bonds, if it's present in the molecule, so it's not oxygen and hydrogen in the molecule, you must have an OH bond or NH bond or FH bond. This is going to give hydrogen bonding, H bonding. For hydrogen bonding is the strongest among these three type of intermolecular forces. Then is dipole-dipole interaction, and the weakest one is London dispersion. So if your molecule is polar, it's going to have a stronger intermolecular interaction or intermolecular forces compared to molecule that is non-polar and has only London dispersion. If it has hydrogen bonding, it's going to be much stronger intermolecular force. What is intermolecular force? What are intermolecular forces? Intermolecular forces are the forces that holds the molecule together. Let's say if you have a cup of water and a beaker of water, preferably, and then you are going to heat up this water. The water molecules that are in this cup of water or beaker of water, container of the water, they are attracted by surrounding water molecule. And every hydrogen is attached to oxygen from a different molecule. So the bond that is between oxygen and hydrogen of the same molecule is shown as a solid line. The bond that is between oxygen and the neighboring hydrogen, or a hydrogen from the other molecule, is, I'm going to mark it like a red color. So that color indicates that this is not a solid bond, but is a bond that is holding two molecules together. The stronger this bond is, more heat you need to break it, because when you try to vaporize or boil the water to go to the vapor phase, you have to overcome the intermolecular forces. So water molecules are holding each other with the strong hydrogen bonding because you have too many of them. So every oxygen is going to be attached to another hydrogen, or attracted by another hydrogen from neighboring molecule. Now, what is this attraction? This attraction is electrostatic attraction, is attraction between opposite charges. Hydrogen bonding, when you have the OH bond and you have like an NH or FH bond, the charge separation is greater between the oxygen with the negative and the hydrogen, which is a partially positive. So this charge separation has a higher value, is more significant. As a result, the bond, or the hydrogen bonding that is between molecule of one oxygen of one molecule and hydrogen of neighboring molecule, is going to be stronger. So if your molecule is a polar molecule, let's say you have a HCl, you get the partially negative, partially positive, and another molecule is going to be aligned oppositely. So you have Cl and H here. So you have a partially positive and partially negative charge here, and these two molecules are going to attract each other. The red color again is going to show attraction between the opposite charges of two separate molecules. So that's why it's called intermolecular force. Now, the more polar this molecule is, then the stronger the bond is going to be. Stronger the bond because of the dipole-dipole interaction that you have for that molecule, for the polar molecule. Now, there were a couple questions. One is HCl hydrogen bonding? The answer is no. Why is not? Because HCl is not HF, HO, or HN. Only these three can form hydrogen bonding. So if it's not one of these, it's not hydrogen bonding. And then the other question that I got is, what about ionic interaction? So if you talk about the general intermolecular forces, we have 4 different types of intermolecular forces. Ionic interaction. And then for molecular compound, you have these three. Ionic-ionic interaction, unless you're talking about the salts in organic chemistry or organic molecule, the salt of the acid or salt of a base, we do not have ionic-ionic interaction because it's specific to metal, non-metal, and ionic compounds. For molecular compound, so you are right, we do have ionic-ionic, and that is the strongest, but when we are talking about molecular compound, these three are the major intermolecular forces, and it goes strongest is hydrogen bonding, then is dipole-dipole, and the last one is London dispersion. So intermolecular forces is going to affect the boiling point, is going to affect melting point, is going to affect vapor pressure. So any physical property or behavior of the molecule is going to be affected. So we can use the intermolecular forces to compare the boiling point of two given compounds. We can predict the physical property. So let's see if we have explanation of different one, and then I will answer your specific questions. If I forget about your question, you have to post it one more time, but for now I remember. So a dipole-dipole interaction exists among polar molecules, and as I mentioned earlier, your polar molecule is going to have a positive side and a negative side, so partially positive, partially negative, and the charges is going to be between opposite charges. So opposite side of the molecule, opposite charges, opposite sides of the molecule is going to attract each other. And this attraction, there's nothing other than in the electrostatic attraction. Basically, is attraction between opposite charges. Because your polar molecule has this positive negative charge permanently, then is going to attract the molecule adjacent to that, just opposite side. So as I said earlier, HCl, one HCl is going to align with another HCl like this, and then you get the attraction. Or HCl is going to attract another HCl from this end. So chlorine hydrogen attraction. That's for polar molecule. So if you find out that your molecule is polar, right away, you could say it's going to have higher boiling point compared to alkane. Now, we have to always compare. The comparison is going to be like apple to apple comparison. So if you're talking about a molecule that has similar like mass, so we have molecules that they have 5 carbons, and then one molecule does have oxygen, the other one doesn't have oxygen. One molecule has the OH bond, the other one doesn't have OH bond. Or if you have 5 carbon alkane, which is carbon hydrogen only, and another one that is polar. So the more polar the molecule is going to be more, that's okay, is going to be a stronger intermolecular forces and higher boiling point, higher melting point, is going to affect viscosity, is going to affect osmosis pressure, is going to affect density, and is going to affect many of the physical properties. It's not just the solubility, it's not just the boiling point though. Okay, so we have a table here that is comparing few of these molecules. A molecule with 4 carbon, no dipole. Why this is no dipole? Because it's only carbon and hydrogen. Compared to a comparable molecule that you have 1 chlorine in the molecule. So this molecule is polar, and because it's polar, the boiling point is 35 degrees higher. So the top one is gas at room temperature, then we have liquid at room temperature, and another molecule of acetone with the CO double bond. With the CO double bond, the value for this vector or the polarity is higher, and with the higher polarity, you have higher boiling point. So polar molecules, they are going to have dipole-dipole interaction as their major intermolecular force, and is going to have higher boiling point compared to compounds that are non-polar with the same number of carbons. London dispersion. What is London dispersion? London dispersion, it's the bond, is the electrostatic attraction that is induced for molecules that they are non-polar. So if you have a molecule with even distribution of electrons, so if the electrons are distributed evenly like this, there is no charge separation. You don't have a positive negative charge. You have a neighboring molecule with the same condition. You have no charge separation. So under normal condition, there would be no attraction, at least no electrostatic attraction between these two molecules. But if this molecule is disturbed, how you can disturb a molecule? You can make the molecule to hit the other molecule. How you could do that? You can lower the volume, you can lower the temperature, you can increase the pressure. So the size of the molecule increases. If the size of the molecule increases, then it's going to be a little bit more clumsy and it's going to hit another molecule. So when the two molecules get close to one another, the first thing that is going to be affected is the number of electrons. These electrons, they have negative charge. The electrons on the neighboring molecule also is negative charge. So when it's affected, it's going to push the electrons away. If the electrons are pushed away, so you get like slightly different arrangement of the electrons. So you get positive charge here and negative charge on the other end of the molecule. So if you get negative charge on the other end of the molecule, if you get negative charge here, this is going to affect is like a domino effect, is going to affect the other molecule, because now we have more negative charge on the left side of this molecule, is going to push away the electrons for the next molecule to the other. And when this happens, you create a negative charge here, and that is going to push the electrons away from the next molecule. So with this domino effect that you have is like an induced polarity. So, and it's temporary, it's not permanent, because your molecule to begin with, it was a non-polar molecule. Even though these charges that are created, they are temporary, they are strong enough to attract and to be attracted. So you have positive charge for this and negative charge. Now there is that in here between these two ends. You have a positive charge here. It's induced, but now it's there. And then you have a negative side here. So there will be attraction in this area. So London dispersion is not unique to only nonpolar molecules. London dispersion exists among every single molecule. Every molecule has London dispersion. But for nonpolar molecule, that is the only intermolecular force. So if you have a compound that is polar molecule, it has dipole-dipole interaction and London dispersion. If you have a molecule that has hydrogen bonding, it's going to be hydrogen bonding and London dispersion. And if it's polar, it's going to be hydrogen bonding. So it's going to be hydrogen bonding, dipole-dipole, and London dispersion. But it's like the priority goes for polar molecule, it would be dipole-dipole. because it's stronger than London dispersion, but it's understood that London dispersion is going to exist among all molecules. Keep that in mind, because if you have two molecules that they both have same polarity, and one has higher boiling point than the other one, that is coming from the second intermolecular force, which is the London dispersion. So we have to now look at the pattern, how London dispersion changes among the molecules that are nonpolar, which nonpolar is going to have higher London dispersion. And let's look at these examples we have here. Ethane is nonpolar, and how many carbon do you have for ethane? Ethane is just 2 carbon, right? Very good. Ethane, this one has only 2 carbon, and hexane has 6 carbon. If you have 2 carbon for ethane, and for hexane you have 6 carbon, and then this is like a huge molecule with more than 15 carbon, is going to be solid at room temperature. Hexane is going to boil at 69 degrees Celsius, but ethane is going to boil at minus 88 degrees Celsius. What type of intermolecular forces you have for ethane? What do you need to know? Before you answer that question, you have to say, is this molecule ionic? And we're just going to simplify and say we're not going to discuss ionic for organic molecule. Is this molecule polar? If it's polar, it's going to be dipole-dipole interaction. Is polar? Is this molecule polar? CH3, is not polar. So if it's not polar, it's going to be London dispersion is the only type of intermolecular force you have for ethane. What about for hexane? Hexane is CH3, CH2, CH2, and CH3. Is hexane polar? Hexane is not polar either, because it's only carbon hydrogen. Any organic molecule that is made of only carbon and hydrogen is non-polar. So also London dispersion for hexane. How come hexane has higher boiling point? Because hexane has larger mass, greater number of carbon. So London dispersion increases with increasing mass or number of carbons of the molecule. So 2 carbon going to 6 carbon, the boiling point increasing significantly. And it's going to be solid and boils at 391 because of that huge molecule. The size of the molecule affects the London dispersion. There are 2 factors that affects London dispersion. One is the size of the molecule, and the other one is branching. How does branching affect? Branching, this molecule here, normal pentane, doesn't have any branch, and the isopentane, 28 degrees Celsius, lower boiling point with 1 branch. And if you have 2 branch, and in organic chemistry, when we talk about branch, is like anything that is attached to the main carbon chain. So it has to be like, you look at the connections, like when you're counting 1, 2, 3, 4, 5. So if I was going to count it, I didn't have to move the curve to count. But here, 1, 2, 3, 4, I'm just sliding from one to the other carbon to count. I have 4 carbon in the main carbon chain, and then if I want to count the CH3 that is attached to carbon number 2, I basically have to move the marker so that is connected to a carbon chain. Is not consecutive, is not continuous. So it has to be continuous carbon chain. I can start from this CH3, go down, or go straight, but anyway, it's going to give me 4 carbon. in this case, for the neopentane, I have 3 carbon in a row only, 2 and 3. I have 2 branches. Branching is going to lower London dispersion forces. So if I have molecule with 2 branches, it's going to have lower boiling point because London dispersion is weaker for branch molecule, and we are dealing with the same number of carbon. So one is mass, that is the primary factor for affecting London dispersion forces. Secondary factor is branching. Isopentane. If it's isopentane, you will learn very quickly soon, at the beginning of chapter 3, that when you say pentane, that means you have only 5 carbon. So you cannot have more than 5 carbon for the pentane molecule, and everything else is going to be branch. I didn't get the actual question. Let me. I used a couple example here. So can you tell me which one has higher boiling point? And tell me what are the intermolecular forces for A, B, and C? Are they the same or they are different intermolecular forces? They are all the same? All London dispersions. Very good. They are all London dispersions. So which one has higher boiling point? A, I think Jordan answered already. A has higher boiling point than which one comes next? B, maybe not. Why not? Which one takes the priority, the size or the branches? Size takes the priority. So if you compare the size, this one is a non-polar with 4 carbon. This one is non-polar with 4 carbon. This one is non-polar with 3 carbon. So first we have to compare these two. And between A and C, same number of carbon, same intermolecular forces. A doesn't have branch, so it's going to be higher boiling point compared to C, as C has a branch. And then between B and C, B has 3 carbon, C has 4 carbon. So B is going to be the lowest. So B would have the lowest boiling point, A would have the highest boiling point. A different example. Which one has higher boiling point? What type of intermolecular force you have? That should be your first question before you answer this. What type of intermolecular forces we have for A? A has hydrogen bonding. Thank you. And B? What type of intermolecular force we have for B? There is a polar bond here. Your oxygen is going to have, because there's a polar bond here, is going to be dipole-dipole. What about the mass? You see you have 2 carbon and OH, 1 oxygen. You have 2 carbon, 1 oxygen, and 6 hydrogen for both of them. So molar mass is the same for both of them. It's like 46 for both of them. So in terms of the London dispersion, is going to be almost the same, but you have H bonding versus dipole-dipole. Because H bonding is stronger, then A is going to have higher boiling point compared to B. If you want to know the numbers, This is going to boil at 78 degrees Celsius, and this one 35 degrees Celsius or 16 degrees Celsius. That's the dimethyl ether. This ether is gas at room temperature, liquid at room temperature, 78 degrees Celsius, 16 degrees Celsius, because hydrogen bonding and dipole-dipole. So you look at the intermolecular forces for both of them, and if the intermolecular force is different, you go with which one is stronger. And intermolecular forces is going to take the priority, is the primary factor, is not the secondary factor. I'm going to give you one more example. Okay, which one has higher boiling point? Why is A? What type of intermolecular force do you have for A? Hydrogen bonding, very good. And B? B is also hydrogen bonding. So same type of intermolecular force. So what makes A to have higher boiling point than B? The larger the carbon chain has a larger molecule. So London dispersion is going to be greater for A compared to B. So hydrogen bonding is the same for both of them, but one has London dispersion, greater London dispersion. Now I'm going to add a compound C here, CH2OH and a CH2OH. Where should I place compound C? What is the difference between compound C? Smaller than B? No. You have 2 OH, right? You have 2 OH, so that is going to be the double the effect. Is going to have highest boiling point. It's going to be very good, very good. So it's going to have highest boiling point because you have 2 OH. That means that's acting like a double the hydrogen strength of the hydrogen bonding. And since hydrogen bonding or intermolecular forces takes the priority over the size, then this is going to be stronger intermolecular forces and is going to be higher boiling point. I'm going to squeeze a compound D here. Compound D is going to be 1, 2, 3, 4, 5, and 6 carbon. Where should I place compound D? With 6 carbon. So what's the first question you're asking yourself? Is the type of intermolecular force. What type of intermolecular force you have for compound D? London dispersion is the only because it's only carbon and hydrogen, so it's going to be London dispersion. And because its London dispersion is much weaker than the hydrogen bonding takes the priority, and even with the 6 carbon, still is going to have the lowest boiling point. Okay, if you had here maybe like 15 carbon, and it gets complicated, then you have to have numbers. So it's not like apple to apple comparison is not a good question. So you have to have actually value for the intermolecular force in order to answer the questions. But up to like 5 different carbon, a difference in the number of carbons, you can go with the stronger intermolecular forces. Okay, perfect. We talked about already about the hydrogen bonding, so we're just going to make sure that you understand the hydrogen bonding is between oxygen of one molecule and hydrogen another molecule, or hydrogen of one molecule and nitrogen of another molecule. So you must have a NH bond, you must have a OH bond for the molecule to give you the hydrogen bonding. Now, if you have a hydrogen bonding coming from OH, hydrogen bond coming from NH, which one is going to be stronger? You look at the electronegativity between oxygen and hydrogen, the difference, and nitrogen and the hydrogen. So electronegativity difference for oxygen is greater than the nitrogen. So because you have greater electronegativity, the size of the charge separation, or the value for charge separation for OH, is more significant than NH. So I'm just going to put a smaller delta here. So because intermolecular force is electrostatic attraction, the greater the charge separation, the stronger the attraction is going to be. So hydrogen bonding caused by OH is going to be stronger than hydrogen bond caused by NH. If your molecule has two OH functional group, like ethylene glycol, the example that I had earlier, CH2OH, is actually, this one is actually used as an antifreeze in the car, and is going to be I think 180 degrees Celsius, a boiling point. That's a huge number because of the two OH bonds that you have in the molecule. The question is, what about HF? So yes, the only difference is that if you have a HF, that means is not part of an organic molecule. So HF is kind of standing alone, separately. The size of the molecule, the difference in electronegativity is going to affect. So you will have the stronger hydrogen bonding when you have greater charge separation for HF compared to NH and compared to the OH. But again, it's not going to be as a separate question. So if you have just the NH and FH, FH is going to be stronger, but it doesn't apply to organic molecule because it's not going to be part of the molecule, because each one of them, they can only form one bond. So there is nothing else attached to the fluorine on that side. Very good. Okay, if you compare here, oh, it's not even 16 that I had. I take it back. It's minus 25 boiling point for dimethyl ether. And dimethyl ether, it's dipole. It has dipole interaction, but ethanol here has the OH bond with the hydrogen bonding. You have hydrogen bonding for alcohol versus hydrogen bonding for amine. Because the hydrogen bonding coming from NH is weaker than the OH, it affects the boiling point significantly. So there is a hydrogen bonding in this molecule, but when it's compared to the molecule that has a bonding coming from OH, is going to have lower boiling point. Now, if you compare this to CH3, CH2, CH3, which is propane, this is going to be much higher than the propane, because propane has only London dispersion, and this one is hydrogen bonding. So this is going to be gas at room temperature, so the boiling point is way below 0. But the amine is 17 degrees Celsius. So solubility is affected by the intermolecular forces. The more polar the molecule, the more soluble in in water. Ionic compounds, they dissolve in water because there's a strong attraction between the negative side of the water molecule and positive ions, and positive side of the water molecule and negative charge from the ionic compound. Basically, when you add ionic compound, it's going to hydrate and it's going to separate unless you have an insoluble compound. By nature, that means the bond between those ions that are insoluble compound, like calcium sulfate, is going to be stronger than the attraction that is caused by water. And again, you may not deal with the ionic charges or ionic interaction in organic chemistry, but know that that is the strongest type of intermolecular forces. And if you have a acid in the lab, let's say, and you want to change that to, that is liquid, you want to change that to solid, you make it combined with the base and changes to salt of the acid. When you have salt of the acid, then becomes ionic compound. Then it changes to solid at room temperature because it's going to have a stronger intermolecular forces. So the more polar compounds is going to dissolve in polar, and then non-polar is going to dissolve in non-polar solvents. Because there is no attraction between them, so it's not similar intermolecular forces. They must have similar intermolecular forces in order to dissolve. Okay. Jordan, you had a question earlier. It was about carbon with the double bond, and then you had the carbon with the only single bond. Can you read the question? I guess. It was an example. I cannot find it. What that, did I answer your question or no? London dispersion. I guess your question was about the London dispersion, and the London dispersion is going to be affected by, yes, I think it was one with the long carbon chain. Yes, the longer the carbon chain is going to be a stronger London dispersion. Perfect. So if you have 6 carbon chain versus 5 carbon chain, 6 carbon chain is going to have higher than the 5 carbon, and if you have 6 carbon but not in a straight carbon chain, it behaves like a non-polar molecule. It has a polar. It's like at that point you're talking about the head and tail. Let me finish with this one, and then I answer Amanda's question. So 6 carbon straight, 6 carbon branch. So if we have an A and B with C, in this case, A is going to be greater than C than B. So the size of the carbon chain is going to take priority over branching. So between A and C, A would have higher, but between B and C, C would be higher than B. Okay, when we talk about the organic molecules, let's say you have this compound here. So you have carboxylic acid with 1, 2, 3, 4, 5, 6, 7, 8 carbon. This molecule is going to be, it's not going to dissolve in water because the number of carbon is 5 or higher. You have more than 5 carbon in the molecule, so it's not to dissolve. Now, is it considered non-polar molecule? Instead of saying this molecule is non-polar in organic chemistry, we have to say that it has a non-polar tail, but a polar head. So this side is polar, polar head and non-polar tail. So the polar head can engage with another polar head of another molecule. Non-polar side can dissolve in non-polar solvent. So it's going to kind of be mixed feeling here. So it's not the whole molecule. So if the non-polar tail is long enough, it takes the priority. So generally the molecule is going to be non-polar. If the non-polar tail is short or small, then the polar head is going to take the priority. So it's going to behave with behave like a polar molecule, and it would dissolve. So in terms of the chemical reactions, to answer your question, Amanda, in terms of the chemical reaction, we still have a polar molecule that can react, for example, with the nucleophile, with the electrophile. So this is a positive charge here because electrons are pulled by the oxygen. So if you bring a nucleophile, something that is attracted to the positive charge, it can actually attack this. It can form bond with this one. But if you put this in water to dissolve it, it's not going to dissolve. So toward chemical reaction, it still is polar. But toward solubility in water, it behaves non-polar. You're welcome. Okay. Any other questions? The functional groups. Now, we had so far what we had was a review, and not everything, I'm sure, was covered in every general chemistry class. So some of the materials were new for you because it wasn't covered in general chemistry, and others were reviewed for you. But those are the general chemistry knowledge that you do need to start your organic chemistry. So starting from next chapter, when we are talking about families of organic molecules, you have to predict the boiling point melting. So you need to go back and use the knowledge what you learned about intermolecular forces in order to predict the boiling point, melting point, in general physical property and solubility of those, and also for like hybridization and strength of the acids and all that. So from now on, we're starting new chapter or new topic of organic functional group. So we want to learn about functional group and then classify each one of them. Then we are going to study each family in a chapter or two. So what is functional group? Functional group is any group of the elements, one element or group of elements that is going to give a specific property or a specific family name or a specific behavior to that molecule. So if you have a Cl attached to carbon, that would make the carbon like a halide. That's like in general coming from halogens. If you have a OH attached to carbon, it's going to make your molecule like alcohol. So it's a function. So OH here is called functional group. So if you have NH2 attached to carbon or carbon chain, so this doesn't have to be one carbon, it could be many carbon, then you have your amines. You have a CC double bond that would make it like alkene. And let's just go over the different type of the functional group by the name. So functional group is the element or group of elements that give a specific property to the molecules, and you can classify those molecules as one family. So we have three classes of the organic molecules. We have hydrocarbons. What does hydrocarbon mean? Hydrocarbon means that it's made only from hydrogen and carbon. So your molecule contains only carbon and hydrogen. Then you have compounds that they contain oxygen. That could be a functional group like alcohol, acid, ether, ketone, aldehyde. And then you have compounds that they contain nitrogen. So what are hydrocarbons? Hydrocarbons, first class of hydrocarbon is going to be alkane. And with the alkane is only carbon and hydrogen. They're all single bonded. If they're all single bonded, we talked about hybridization. Hybridization for all of all the carbons is going to be sp3. If the hydrogens are written, fine. If it's not written, you have to add enough hydrogen to make it 4 bonds for each carbon. Cycloalkanes, they are cyclic system, so it's going to be a bond between head and tail carbon, and it's going to form a ring, and is cycloalkane. Hybridization going to be sp3. Then we have alkene. Alkene has a CC double bond, and if it's CC double bond, that if we have carbon with 1 pi bond, it's going to sp2. Cycloalkene. Cycloalkene is a cyclic system, also has a CC double bond. Alkyne is going to be CC triple bond, and we talked about the CC triple bond being sp hybridization. And then aromatic compounds, those are the compounds that they have benzene ring. And you learn in organic chemistry too more about aromatic compounds, that what other conditions are have to be met in order for compound to be aromatic. But it's a cyclic system with conjugated pi bond. That means that there is a double bond, single bond, double bond, single bond, double bond, single bond, and it kind of rotates. So this pi system is going to start moving around, and sometimes they are just putting a ring inside the 6-member cyclic system, and that shows aromatic. At this point, for you, you need to be able to recognize the functional group. Is not to know what makes this molecule, at least for chapter 2. So let's look at a couple of these examples. What is the functional group for this molecule? If you can see there, what is that? Alkene, because you have a carbon-carbon double bond there. This carbon-carbon double bond makes the molecule alkene. This is a cis alkene, and we have a trans alkene. So both of them are alkene. What about this one? Also alkene, because the only functional group that you have there is a CC double bond. And same here, alkene CC double bond. If you look at this, the plane of the CC double bond, you see one chain is going, one side of the molecule is going to go up, and the other one is going down. That's why it's called the trans alkene. So it doesn't always have to look like a straight line for you to recognize it. So you are going to just look at the double bond and see if the 2 branches that are attached is going to be on the same side or opposite side in order to determine if it's cis or trans. What about this molecule here? Why is it so small? What is that molecule? What's the functional group for the molecule? Is not a triple bond. This one has, this one is a conjugate. When you have a cyclic system with alternate double bond like this, conjugated, you have 3, and this is unique to benzene ring. If your molecule contains the benzene ring, then it's aromatic. So this is going to be aromatic. So this one is aromatic. Oxygen containing compounds, we have alcohol that has OH. Ether, another functional group. Ether is functional group that oxygen is attached to 2 carbon. This is the functional group for ether. So when you see oxygen single bonded to 2 carbon, 1 on each side, then is ether. When you see alcohol, that means OH is attached to carbon, then is alcohol functional group. Aldehydes and ketones, for aldehydes and ketones, when you have a CO double bond, if it's attached to 1 carbon and 1 hydrogen, is going to be aldehyde. And if it's CO double bond attached to 2 carbon, is going to be ketone. So aldehyde, so when it's oxygen containing oxygen single bond, it could be OH, or O attached to 2 carbon, you have alcohol or ether. Then if it's the CO double bond, it could be aldehyde or it could be ketone. And COOH, if you have a CO double bond that is attached to OH in one side, and the other side it could be hydrogen or it could be carbon, this is carboxylic acid. If you remove the H, you add Cl, is going to be acid chloride, because basically you are removing the OH from carboxylic acid to add the Cl. So if it was just the OH, it was carboxylic acid. Now you're replacing OH with chlorine, is going to be carboxylic acid. Acid chloride. And if you remove the OH and you replace it with OR, basically one part of the alcohol. So let's say you take the hydrogen away from alcohol, then you have OR. OR. What does R stands for? The R is, it can be hydrogen or it can be any alkyl group. Any alkyl group. And what is alkyl group? I'm going to show you. But so the R, it could be hydrogen or it could be carbon. So when you say R here, that could be carbon. For ester, is going to be OR, is going to be is coming from alcohol. So you have this side of the molecule. If you place OH, it's carboxylic acid. Now you change the OH OR from alcohol, then you get ester as the functional group. Amide, you take the OH and you place NH2. That would be amide. Eventually, you have to memorize them all. Amines, but for now it's just to recognize. But if you just go with like a hydrocarbon and then memorize those, and then oxygen containing, then you have only 4 groups to R is just a placeholder. Yes. Thank you. And then nitrogen containing compound, they could be amine or it could be amide. So amine functional group is the CN. So if you have a C single bond to N, and then it's attached to either carbon or hydrogen, so it's attached to R groups only, then it's going to be classified as amine. So you could have hydrogen attached here, but there must be at least one carbon nitrogen single bonded in order to classify as amine. So here is the carbon nitrogen, and then in this case we have 2 carbon nitrogen, but I said you have to have at least 1 carbon nitrogen bond in order for your molecule to be classified as amine. Amide is the CO double bond that is attached to nitrogen. This is the functional group for amide. And to this, you could have either hydrogen attached or you could have carbon attached. But the part that it makes the molecule amide is a CO double bond, single bonded to nitrogen. Okay, let me see if we can do a couple examples here. These are just the sample questions, basically, or for practice. How do you determine the hybridization? What makes this carbon to be sp2? Because the answer is there. I cannot ask what's the hybridization. So why this is a sp2 hybrid carbon? What are you using? What information you are using to determine hybridization? One double bond. Okay, one double bond. If carbon carries one double bond is sp2 hybridization. But in general, if you were trying to find it, you are going to count the electron domain. Remember, electron domain. If you have 3 electron domain, is going to be sp2 hybridization. And for electron domain, CC double bond counts as 1, CC triple bond counts as 1, CC single bond counts as 1, and pair of unshared electron counts as 1. So this is the table I asked you to make sure to write somewhere yesterday. And if you have 3 electron domain, is going to be for 3 electron group or electron domain is going to be sp2. So this carbon here is sp2 because you have 1, 2, and 3 group attached to the carbon. So it's going to be sp2. What makes this carbon to be sp? You have only 2 electron domain here. One is a triple bond, which counts as 1, and one is a single bond, which counts as 1. But for 2 electron domain, is going to be sp, because you have 2 electron domain. No double bond, it would be sp3. One double bond, it would be sp2, and 2 pi bonds is going to be sp. So if you have 1 pi bond, it would be sp3. No pi bond would be sp3. No pi bond, what we talked about yesterday also. The single bond versus double bond versus triple bond. Can you tell me which one is stronger? B or C? Which one is a stronger bond? C is a stronger bond. Okay. Which one is shorter bond? Shorter. Short bond is a strong bond. They get closer. The bond is stronger. They actually get closer to one another. This is a short bond. It's a strong bond. Triple bond is the strongest, and it is the shortest of the 3. So if you say is triple bond between the single bond and double bond is stronger. But if you are comparing pi bond and sigma bond, pi bond is weaker than sigma bond. So pay attention to the question in case if you have that. Pi bond is weaker than sigma bond because pi bond is coming from side-by-side overlap, and sigma bond, it comes from head-on overlap. So there is no gap here. This is a sigma bond between 2 orbital. This is a pi bond between 2p orbital parallel, and this is a head-on. So sigma bond is stronger than the pi bond. But double bond is stronger than single bond because double bond is 1 sigma plus 1 pi. The S character, greater the S character, the stronger the bond also. because you have, for sp hybrid, you have greater s character. It's making also this hydrogen more acidic. Acidity, it's not the question here, but we had it before. sp hybrid carbon carries more acidic hydrogen than sp2 than sp3. So if your carbon is sp hybrid, the hydrogen attached to it is going to be more acidic also, more acidic. So it's comparing the hybridization. You have your bond angle for each hybridization, the bond length, and then the strength of the bond. Even the bond length to the hydrogen is greater compared to when you have a sp hybrid. So if you look at the pattern here, the length of the CC bond is going to increase from sp to sp2 to sp3, or opposite is going to decrease. The bond angle, we talked about these. You need to know the bond angle. You don't have to memorize the actual numbers here for the bond length. You need to know the pattern, which one is shorter, which one is longer. For the strength of the bond is increasing from single bond to double bond to triple bond. You don't have to know the exact number for in terms of the kilocalorie per mole energy needed to break, but you need to know the pattern. For triple bond, is going to be much higher than double bond than the single bond. And the same here is the pattern that you need to know. The length is not much of a concern, but the only thing that you want to know for acidity, if it's a sp hybrid, that hydrogen is more acidic than the other. Length of the bond, no, you don't have to memorize exact numbers, but what you need to memorize is the pattern. So if you go from single bond, double bond, triple bond, the bond is going to be shorter. Okay, the functional group. This is just a review. We already talked about it. If you have alkene, the functional group is in the blue color part of the molecule, and that is a CC double bond. That's the functional group. So if you were given like a large molecule, which you should have it in OR app assignment, it's if it's asking for functional group, is looking for anything other than carbon hydrogen or carbon carbon single bond. For alkyne triple bond, the functional group is going to be CC triple bond. Alcohol, functional group is COH, because if OH is attached to sulfur, it's not going to make it alcohol. If the OH is attached to carbon, it's going to make it alcohol. Ether, when you have the oxygen attached to two carbon with a single bond, then it's going to be ether. So basically, if you take the water molecule, you replace one of these hydrogen with carbon, is going to change to alcohol. If you change both of them to carbon, it would change to ether. Haloalkane or alkyl halide, it has the functional group of halogen attached to it. And these are some of the examples. At this point, you don't need to know the name for this compound. For chapter 2, you will start learning about the names in chapter 3. Amine functional group, if you have a CN single bond, aldehyde functional group is going to be is going to be CO double bond attached to carbon on one side and hydrogen in another side. Ketone, CO double bond attached to two carbon. That makes it functional group. So if you're asked about functional group for ketone, you cannot say CO. It must be attached to two carbons to be ketone. Carboxylic acid is going to be CO attached to carbon or hydrogen or R group, like a placeholder, as you said earlier, and OH on the other side. So COOH is the functional group for carboxylic acid. Okay. So you need to know the functional groups for different families. So you should be able to recognize them. pKa value. What is pKa value? It determines the acidity, which one is like more acidic. The most acidic organic molecule is going to be carboxylic acid. This is we don't compare organic molecules to inorganic acids. Inorganic acids, you deal with their pH and concentration and all that. But when you are talking about organic compounds, carboxylic acid is the most acidic organic molecule. Then is the phenol. Now, do you have to know? Okay, that was exactly what I was trying to say. Do you have to memorize these numbers? No, you don't have to memorize the numbers. But if you were asked why this is acidic or more acidic, remember the four factors that we talked about: acidity or strength of the acid. One was resonance. So if you compare this molecule, carboxylic acid, with alcohol, you remove the hydrogen. The lower the pKa, yes, it is a stronger acid, exactly. So if you remove the hydrogen here, you end up with a CH3O. There is no resonance for it. But if you remove this one, this hydrogen, you end up with a COO minus, and you can form a resonance. So basically, you get the pair of electrons to share double bond for the carbon, and this pi electron moves up, so it forms a resonance. And when you form the resonance, then you can get the stronger acid, because the conjugate base, which is the acetate after losing the hydrogen, is going to be stronger. And then other factors that we talked about. So your question, you don't have to memorize it, but if you're comparing, you should be able to compare and use the factors that affects the acidity. Which one is more acidic? I'm going to label this A and B. Which one is more acidic? A or B? Yes, resonance increases the acidity. B is more acidic, and because? Why is more acidic? Hybridization. No, hybridization, if you didn't have the lower, you have the pKa values. Between A and B, B is more acidic because this carbon carrying the hydrogen has a sp hybrid, and the carbon from A has a sp2 hybrid. So you need to know this factor that affects the acidity. If the more S character of the carbon attached to the hydrogen, is going to be, yes, triple bond makes it sp hybrid, or more S character of the hybrid for the carbon is going to make it more acidic. So comparing to sp, sp2, and sp3, sp has higher acidity compared to the sp2 and sp3. What is this functional group here? carboxylic acid. Carboxylic acid. What is this functional group here? Alcohol. And what is this functional group? In general, you call them halides. So it would be like halides attached to the ring, halogens attached to the ring. And this one, aromatic. Benzene ring, which represents aromatic compounds. Yes, benzene aromatic ring. And last one of this structure, the blue box. Is that amine or amide? Okay, if we had CN bond without the O double bond here, it would have been amine. But like this one here is amine. But because you have the N attached to CO double bond, is going to be amide. So if you see the CN, you have to look at the neighboring carbon. If it's a CO double bond, it would change it to amide. And then if there is no CO double bond attached to it, it's going to stay as amine. At least one CN single bond, it makes it amine. You could have more than CN bond, one CN bond, but at least one would make it amine, because then nitrogen and carbon can be attached to either hydrogens, or it could be attached to other carbons. And you will learn later that if it's two CN bond, that means nitrogen is attached to two carbon, that basically that amine is called like a secondary amine. But you don't have to know that just yet. Okay, your questions and your concerns. Any questions from the chapter? Chapter 1 or 2? 2, very good. And let me see, what was the rest of the question? If it was from the lecture from yesterday, sure, but for today, I think it's better for you to go back to the PowerPoint and the book, try to find it, because if I give you the answers now, then it's not going to help anybody else to look for, because when you go back to the book and you look for the sample problems, it's going to make you to read that section again and understand. But if there's something from yesterday that you couldn't answer the question, sure. Understand resonance structures. Resonance structures. Okay. Can we review the quiz after? Can be reviewed on Monday? Because I have one student who I didn't get an email from, or it was like after midnight that I haven't checked, and I want to know what happened. With the resonance structures 4, 5, 6, and 7, is this from OR chapter 1? Sure. Okay. Anybody else can help with those questions with the 4, 5, 6, and 7 with the OR, with the resonance? Okay, let me question number 4. I'm going to campus later and I will print those because I don't have a printout. Then I take a picture to post explanation, not the answer. So, okay, it's the bonds moving around to stabilize the molecule. Yes, exactly. Lewis and the bases. The Lewis base, you mean? The Lewis base? Lewis base is acids and bases. Acids and bases. That is a for acid, you do need to know the acids and bases. So there are 4 factors that you are going to compare to see between the 2 acids which one is stronger. So one was electronegativity. I said if you're going across the periodic table, OH, and then you have NH on this side, you have HF, electronegativity is stronger, is going to be a stronger acid, electronegativity of this element. So what I'm going to suggest you to do for that section, do every problem of the book, end of the chapter problem. I know it's a lot of practices, but at least you have access to the solution manual and you see the answer, and it's going to make it easier for you. Okay, I will try to answer some of the questions now. So for size factor, like a HI is going to be stronger than HBr and HCl. That was a factor. Then we had resonance. That was if the conjugate base forms resonance, is going to stabilize the conjugate base. The easier the conjugate, let me put it this way. Acid in general is classified as acid easier to lose hydrogen. If acid loses hydrogen and be miserable, is not going to lose that hydrogen. If acid loses hydrogen and be comfortable, be stable, then doesn't mind to lose the hydrogen. It wants to lose the hydrogen because it wants to act as acid. It's acid, so it wants to lose that hydrogen. Like for carboxylic acid losing hydrogen, then after losing hydrogen, it becomes like this. You see? It forms 2 resonances. So it doesn't mind losing that hydrogen. So it would lose hydrogen and acts like acid. But if you look at the alcohol, like a CH3, CH2OH, after losing hydrogen is going to become CH2O-. There is no neighboring CO double bond or adjacent C double bond for this negative charge to be delocalized. So it's not going to be able to move the charge, and that charge is going to be too heavy oxygen. So this is unstable because cannot form resonance. This one is stable because it can form resonance. So which one acts as a better acid? It would be this one, because after losing that hydrogen, it becomes a conjugate base, and that conjugate base is comfortable, is stable. For alcohol, losing that hydrogen is going to, after losing hydrogen, is going to feel very unstable, miserable. So why should alcohol lose hydrogen? So it's not going to lose hydrogen easily. And if it doesn't lose hydrogen easily, we call that weak acid because it cannot lose hydrogen. So just talking about this formation of the resonance maybe also helps you a little bit with the resonance. Now, if you have a plus charge that on an element that is conjugate with the double bond, that plus charge can move. If you have a negative charge that is conjugated with the double bond, that negative charge can move. But if a plus charge or negative charge that is not conjugated. Now, I'm going to say one more time what does conjugate means. Conjugate, it means that if it's separated by one bond from a double bond. So this negative charge for here is conjugated, this negative charge is conjugated with this double bond here. So if this negative charge, basically pair of electron, it comes down here, okay? If you move the pair of electrons, one pair of electron from oxygen to this carbon-oxygen bond, you are going to make this double bond. This carbon already has 4 bonds. Carbon cannot have more than 4 bonds. So if pair of electron moves here, is going to be 5 bond. You have to take the weakest bond, and that weakest bond is going to be the pi bond that is going to break over this oxygen. So if this pi bond breaks over this oxygen, what is pi bond? Pi bond is made of 2 electrons, so you are going to get 2 extra electrons here, and that gives the negative charge to the oxygen number 2. So oxygen with a negative charge move 2 electrons to this middle part to form double bond with the carbon. This carbon that already had 4 bonds cannot take the additional bond unless it loses 1 bond or loses like 2 electrons, something that makes carbon again with 8 electrons stable is going to break the pi bond, and that pi bond, there's nothing other than just 2 electrons. So those 2 electrons would go to this oxygen. Now, when does resonance forms? If you have a negative charge that is going to be adjacent to double bond. If you have pair of unshared electron that is conjugated with a double bond. So you must have pair of unshared electron conjugated with positive charge, or you must have double bond conjugated with positive or negative charge, because you want to distribute the charges or formal charges, and the only way you can move them around is if you have pair of unshared electrons somewhere, like if nitrogen has pair of unshared electrons and there is a negative charge here or positive charge here, then you can move this to make the CC double bond. So basically this positive charge here is going to be conjugated or is considered conjugated with pair of unshared electron you have on the nitrogen. If you have pair of unshared electrons here and there's a double bond here also, so you can move the pair of unshared electrons, but at this point, when you move you see you have four bonds already for this carbon. When you move the pair of electrons here, then the pi bond is going to move up. So when the pi bond moves up, you get a negative charge on this carbon. So you are working with pair of electrons, you are moving with pi bond, pair of unshared electrons, you are playing with the pair of unshared electrons and pi bonds and negative or positive charges. If all elements of the molecule they have 0 formal charge, there's no point for formation of any resonance. That is correct. So with this explanation, and you just kind of take a step back, please, and go back and read the resonance sections from the book, because the PowerPoint doesn't have enough information. Read it from the book, look at the solved problems. That is going to, just answering one question here, it may not help you to build the skills to recognize a question on the exam. But if you read the section and if you read the examples, you review the solved problems from the book, and I hope you all have a book. You're not going to survive without the book, organic chemistry class. So make sure you have the book. You go back and read the resonance part and look at the solved problems. Keep in mind the explanation that I have with this scenario. When you have pair of ion electrons that is adjacent to a element with positive charge or negative charge, resonance can take place. When you have pair of unshared electron that is attached to element that carries a double bond, the resonance can take place. If you have double bond adjacent to element that has negative charge or positive charge is conjugated, and conjugated means that it's separated by a single bond from a double bond. So if you have a negative charge here, this is a single bond, and here is a double bond. This negative charge is conjugated with the double bond. If you had a positive charge here as separated from a double bond using a single bond, this means is conjugated. So if you have a conjugation, or your negative or positive charge is separated from a double bond by a single bond, so there is a single bond between your positive charge blocking the positive charge from the double bond, this means it's conjugated. So you have to have a conjugated system in order to form the resonance. Okay, good questions though, because it's going to is a major concern. When you have resonance, it's going to stabilize the molecule, but not every resonance is worth it for the molecule. Sometimes you go from one shape to another one, and then you increase the charges. You would do charge separation greater. That's not going to benefit. So that's going to be like a minor resonance. A stable resonance is the resonance that has the lowest number of formal charges or the charge separation. So if you have less charge separation, and if you have like a positive 2 and then minus 2, then you can make it 0. That would be like perfect. If you start with like positive 2 charge in one element, you bring it to positive 1, that's good. But if you go from positive 1 to positive 2, or positive 1 to positive 2, which is opposite, is not good. It's not going to happen. If the positive charge is on less electronegative element, it would make the resonance more stable resonance. Negative charge on more electronegative is going to make it more stable. Octet is very important. So if one of the resonances doesn't have octet satisfied octet satisfaction for all elements, then the resonance is not good. I did write down the question numbers, and I will look at them. I will get back to you because I don't have the printout, and for me to go back and forth, and it's easier for me to print and then write explanation for you. I don't forget those questions. I will take her up. And then your other question, let me write down. So Monday you have a quiz 2. Monday we are going to review for quiz 1 as well. The original structure has a formal charge of 0. It doesn't make sense to make a resonance that makes the structure have formal charge on some of the atoms. If you do not destroy, by making resonance, if you do not destroy if they are all 0, then no, then you don't have to put the resonance. No, if they're all 0. But if they are charged, if there is a charge, formal charge, and moving around, you're not going to destroy the octet satisfaction. The more number of resonances is going to benefit the stability of the molecule. Okay, the greater number of resonances is going to give more stability, as long as the octet satisfaction is. Okay, Very good. We actually, okay, the time is over for the, almost over for class. I was hoping to start the next chapter, but it looks like no, we cannot. We are going to be one day behind the schedule, but okay, I prefer you, you know, get your questions answered than finishing the chapters. But we do have time. We will finish the chapters. So please, at one point, I'm going to start asking you to turn on the camera, maybe on Monday, because I haven't seen any of your faces. I want to, Talaya, I was going to talk to Talaya, she's gone. So make sure you do have a webcam, or you're using a laptop with the camera. Be prepared for that. I'm sure you took the class, you took the quiz with the respondents. The honor lock, unfortunately, is not available, even though they promised for 2 of my exams. I believe for each honor lock, it costs like $20 to college per student, and that's why we have to request it ahead of time. So I did request only for 2 of the exams. It wasn't the right time for me to ask for every quiz and every exam to be on honor lock. And if one of you have problem, then I have to deal it separately. Try to please. I just understand my point of using the other browser lockdown, not honor lock for each one of them, because the cost to college. This is not the right time for me to make it more costly. And same thing for like lab manual. I try to, you know, get it cheaper. Not all of them, just 2 of the exams based on the syllabus. I believe it is exam 2 and the final exam is going to be honor lock. Exam 2 and 4 will be honor lock. The others are responders. The responders, you already have the license, and is it doesn't cost additional. They're both valid. For Nova, I only use the responders though. Is there any way to exempt the final, not the final, but your final can replace the lowest grade on the other exam?